Good morning. It's a wonderful pleasure to be back here in Edinburgh. It's 4 years that I was in this room last, and it was a beautiful workshop where some of the people present were also present. So this kind of is a bit of a deja vu. Pre-pandemic, of course, exactly. I think it was literally the last conference that I could attend in person before the lockdown. Yeah, so thanks to the organizers for arm twisting me into giving an introductory talk on quantum entanglement, which is it's a fantastic proposition to give it in the first place, in the first talk, on the first day. But it's also very daunting. I mean, those of you who have looked at quantum entanglement at all, and it's a subject that has a history of nearly a century. In quantum information alone, which is my topic, which is going to be my take on this talk. There are these 2 review articles that people like to cite. One is simply called Entanglement. It has about 1,000 references, and it's not even up to date. It's more than 10 years old. And the other one is a multi-party entanglement, which also has a few hundred references. It's a bit more recent. And there is no way you can give an entanglement overview or tutorial in 1 hour. So what I do is a bit of silliness. I just pick a few things that I think about when I think about entanglement and that come to mind. Well, some things, not necessarily my work, but some of the things that I got to know over the years. Obviously, there are enough experts in the audience to make me like to hide on the desk. So I hope you're not too bored. I mean, the super entanglement experts, starting with the public lecturer from tomorrow, don't be offended by what I'm going to say. Okay, so I'm just starting with a bit of mathematics, so they can just the modern terminology. What is entanglement and what is the opposite of separable? So we're gonna just deal with, I mean, simple quantum systems. So I will always have some kind of Hilbert space in the back, and I will pretty much always assume that there's some kind of fixed tensor product structure. It's separated into distinguishable degrees of freedom. Those might be internal degrees of freedom of a particle or of a composite system, but they might be like in most of the intuition of most people, they might be referring to separated system in some sense. And so we'll just talk about density matrices, obviously, positive semi-definite matrices on this Hilbert space. For a lot of what I'm doing, I think it's fine to consider finite dimensional, but in general, it will be just a separable Hilbert space. Positive semi-definite trace 1. And of course, the extreme points of this set, it's a convex set. The extreme points are the pure states with state vectors psi. So, and so kind of the terminology goes back to basically to the very dawn of even the word entanglement, to Schrödinger in the 1930s in a series of interesting articles. So so at the time, people were mostly worried about wave functions. So everything was written in terms of pure states and vectors. And so separable state is for them just a product vector. And everything else is entangled in this product Hilbert space. And so, of course, that means that pretty much everything is entangled, because in algebraic, in geometric terms or in measure theoretic terms, the separable states or these kind of separate product vectors, that's a null set. And so then, as far as I was told, the extension of this terminology to mixed state, that's due to Reinhard Werner here. Simply the convex hull of the pure states as density matrices that we call separable, and everything else entangled. And so that's just mathematics. And basically, well, quantum entanglement is about the study of these concepts and well, how they behave under different kind of ways of combining such objects, inseparable or not. So what I will do for the rest of the talk is basically 4 sections, which I feel like one has to cover when talking about entanglement. The first is basically the origin, going back to Schrödinger and the very fundamental paper by Einstein, Podolsky, and Rosen from 1935. So that's 90 years almost now. Then a bit of non-locality, Bell inequalities, etc. And then I will talk about the things that I'm most familiar with, that I feel probably most happy to talk about, entanglement as a resource, and this kind of thing. That's kind of our God that we worship, LOCC, stupid name, local operation and classical communication. I will discuss this mostly in the bipartite setting, as I will show in the beginning. And then for the big end, I will make some remarks about the multi-party. Okay, so the origins of quantum entanglement, I think probably by now this is kind of gone into popular culture, but again, probably tomorrow's public lecture will give a much better job at retracing this. The origins of this are in the discussions in the early days about the foundation of quantum mechanics, what all this really means and how to make sense of it. And some people couldn't make sense of it, and they kept asking stupid questions. And so this is sort of a tiny dialogue with caricatures. I mean, obviously the pictures are real. This is real Einstein. Heisenberg famously has this uncertainty relation. And so one popular interpretation of, in fact, that's kind of more or less how his generation would have said it. You cannot know x and p, the position and momentum of a particle, at the same time. And so that's deliberately vague and provokes immediately a question from the small child, why? Why not? And the Bohr intervenes. Well, as a matter of fact, you cannot, in fact, you must not assign even mentally definitely values of x and p. Already that is a sin. And so that's even worse for the kid. Why can I do this? I mean, what goes wrong if I try? And so Bohr is in a good mood today. So instead of being the stern teacher, he says, look, I mean, we both share certain philosophical ideas. So from Mach, we took this idea that what we talk about in physics must be rooted in experiments. Like our metaphysical concepts, maybe they are free mathematically, but to be physics, they need to connect to an experiment. So for example, X corresponds to a procedure to measure the position of a particle, and P corresponds to another procedure to measure the momentum of the particle. And well, in quantum mechanics, there is no measurement to measure X and P jointly. So that's why you shouldn't try to assign values to X and P jointly. Well, I mean, this may not be a very good representation of Bohr because there's a simple objection, which is precisely to say, well, but there is a measurement for X and there's another measure for P. So it makes much more sense to think that those are values that are sort of potentially there. Maybe the measurement, maybe there's a limitation in nature that prevents me from accessing all of this information, but why shouldn't it be there? It's like, you know, this is just unknown. And so that's where Einstein's kind of story started with. The quantum mechanics might be, I mean, as the formalism, the quantum theory might be incomplete. There might be other mechanisms and other variables at work that provide a more fundamental description than those stupid wave functions and Born's rule that all got Nobel Prizes, but for him, they were all equally useless at some level. Yeah, so Bohr engaged with this kind of point of view, but I mean, basically that's where the two parted. I mean, Bohr simply embraced this fact that there are things that don't exist until you measure them. That's kind of the mantra. And so then eventually that's kind of where the entanglement starts. Einstein and Boltzmann in a very beautiful paper that I think initially was essentially ignored, and now is one of the most cited, the most visible papers in the Physical Review. They came up with the following, a thought experiment. And of course, all of this is thought experiments. So let's consider two particles. And instead of X and P, with the help of Bohm, let's consider this just two spins. So these are two binary degrees of freedoms. And the observables that we look at are just the Pauli Z and the Pauli X unitary. So they have plus and minus one eigenvalues. And so the kind of observations we make are these here. We're looking at observables locally measuring Z on one particle or on the other, or X on the one or X on the other. And so clearly we have some kind of one of these X and P problems here because the Pauli matrices don't commute. In fact, they anti-commute if we are looking at the same system. But of course, Z1 and X2, they do commute because it's like Z tensor 1 and 1 tensor X, wonderful commute. So in quantum mechanics, that means that's kosher. I mean, even Bohr would say, fine. I mean, you may assign simultaneous values to those different experiments. Why? Because there's a single one experiment that somehow implies knowledge of, for example, Z1 and X2. And so what these guys noted was, just calculating away, they noticed, look, Z1, Z2, so that's Z tends to Z, and X1, X2, they also commute. That's because each individual factor anti-commutes, so that minus signs square and then goes away. And so we can actually also assign a simultaneous reality to these two guys. And so Bohr says, yeah, okay, now of course you're talking about a different experiment, but when you're saying about ZZ and XX, yes, that they also commute, so we can also assign a reality to these things. And let's find a joint eigenstate, because these are just 4x4 matrices, so we can diagonalize them jointly. And we find, for example, this beautiful eigenstate. There's the joint -1 eigenstate. That's called the singlet state, and okay, you can write it like this in vector form, so with the plus and -1 eigenstates of Z and of X. I mean, maybe the notation is a bit too physicsy here. And so the story then goes as follows. I mean, I don't want to retrace the philosophical argument here, but mostly the kind of what is kind of the intuitive reasoning here. How do you measure Z1, Z2? I mean, there are many different ways. If you're only looking at this one observable, and this is actually an important point, we can measure if we, up to here. So we got Bohr to admit that, okay, these guys commute. So there's a joint measurement of ZZ and XX. That will correspond to a certain measurement. In fact, in some certain sense, it's unique because those two guys together define a complete basis. But if I just focus on one of them, well, how can I measure Z1, Z2? Well, obviously, I can just measure locally. Alice can measure Z1 and Bob can measure Z2, and then they can multiply the outcomes. That gives you the value. And so what you observe is that locally, these outcomes are random. They're uniform, but their product is -1. So that means once Alice has made a measurement, she can predict in the language of EPR what the outcome of Z2 will be. And likewise for X2 after X1. Of course, it also goes the other way around. And so then the argument was, well, okay, you see, these sites, they could be very distant. They could be space-like separated when they're doing these measurements. And so from physics principles, Einstein and Podolsky and Rosen argued, well, we know that nothing should actually influence the second particle just because I made one or the other measurement. And in fact, it doesn't. And so they say, but something, so that the only way this can be explained in their mind was, okay, there must be something that was present beforehand. And so this was the birth of the hidden variable theories, local hidden variables, even though it was not expressed in these terms. So yeah, so nowadays we regard this as a very fundamental paper. The argument is reasonably simple. Bohr replied to it, and I think that's pretty much sums it up what he said. So I don't buy it because you talk about counterfactuals. First you said XX, ZZ, that's one measurement. But then you said, oh no, Z1, Z2, and X1, X2. There's no world in which I can make all of these measurements. It's nonsense. Go away. And well, almost everybody went away. Schrödinger invented this word entangled for these states. So then I don't parry also the separability here. So which I'm a bit fuzzy on the history. I think he wrote a series of review articles in English and in German. It might be that the English one was his own translation of the German ones or an augmented material. So the German word is verschränkt, which like somehow is more intertwined. It's more something like this. So the properties of the two systems, they are kind of random, but they are intertwined, or as we say, entangled today. And yeah, so here is a little bit of fun that with some students, we recently went over some of these arguments again. I want to show a little simple calculation. So the way this psi minus in this argument is defined as the unique joint eigenstate of these two observers. The two observers, they happen to be local. I mean, each of them individually, it suggests a measurement that you, a procedure of a measurement that you build by doing something on one particle and on the other particle and then pooling the results in some way. I mean, that's kind of a generalized description of what I just said. Measure Z here, measure Z there, and multiply the results, right? So the -1 eigenstate, that corresponds, of course, to the, well, it's actually more than one for each of them. That corresponds to a projector. Here, that's the -1 eigenstate of the ZZ, and here the same for the XX. And so, just like
what exactly do you mean by a separable projector, just to be sure?
In the same sense that it's a positive linear combination of product projectors.
Yeah, well, but
they're probably in the same sense of the density matrices.
Right.
It's in the same sense as the density matrices. It's not product. So they are
linear combination of separable.
Positive linear combination of product projectors. Yeah. I mean, this is maybe not the most interesting observation, but it's just kind of a feature that comes out of this. Why? Because we have this local procedure to measure, right? The +1 eigenspace is composed of the Z up, no, sorry, the -1 eigen, Z up, Z down projector, that's a product, and the Z down, Z up, that's also a product. And so these are two, actually, they're two orthogonal. And so that comes from the fact that this observable is measurable locally, and measure and then do some kind of classical post-processing.
It could be part of an unentangled product basis, right? I mean,
yeah. Yeah, no, that's of course true when you look only at one projector. Yes.
Yeah, okay.
So this one measurement, P and 1 - P, they are both separable. I mean, that's kind of what makes these stabilizer states so interesting. Well, I mean, it's even before, because we can describe them in terms of those product observables. But then when I want to pick out the + or -1 eigenstate of such a product of Pauli's, so it's kind of, there's half of the products will be +1, half of them will be -1. The point is that both of these eigenspaces are projectors, have projectors that are separable in that usual sense. And of course, by construction, they commute, and this psi minus is the unique joint -1 eigenstate. So the product is equal to this one. And so anyway, so the acute observation that I've seen pop up in a very special case in a paper by Holger Hoffmann a while ago, and then in this form here in a paper by Jessica Bavaresco in the group in Vienna. It turns out every pure state in a bipartite system, so every state vector in A tensor B is the joint +1 eigenstate of two separate projectors that have the same, I mean, the same abstract properties. P and 1 - P, Q and 1 - Q, so the projectors and their orthogonal complement projectors are all separable in the sense of matrices. They commute, and their product is this pure state psi. And so in this paper, they massage this identity a little bit more, and they extract this inequality, which is just algebra. This is a simple, basically just comes from the fact that PQ is positive. This makes, actually, don't I have it? No. This makes it kind of experimentally interesting, because you can measure these two guys here by local means, and you can set, I mean, that's what they use it for. They say, well, you can make relatively simple local measurements, and you can certify an entangled state experimentally, in the sense that maybe your conclusion will not be that you got the state psi. That's usually not what an experiment looks like. You get the state psi with error bars. One way of interpreting is, okay, for example, the inner product between the density matrix rho and this psi here, the expectation value, that's the fidelity is something, 1 - epsilon. And so 1 minus the fidelity you can upper bound in this way. And these are quantities that are accessible in the proof. I mean, the proof says a little bit more, accessible in local terms. Okay, so here that's what it looks like. So So we start with this one here. So this state vector in A tensor B, we can always find. So we're gonna choose a correct basis. We always can find a basis where the state looks like this here. So that comes from, I mean, you can start with any basis, and you by singular value decomposition of the expansion of the coefficient matrix. You have your computation basis. You write the psi as a linear combination of, I don't know, I tensor J. The coefficient matrix that has a singular value decomposition. The singular values are those lambda square root of lambda j's, and those two orthogonal bases here, they are just the corresponding bases that come out from the and so the first projector will be just this one here. It's a projector onto J tensor J. So it's clear that psi is an +1 eigenstate of this one when you do the calculation. And then for the other projector, we do kind of what we learned from this EPR Bohm example. We go to a conjugate basis. So this is these coefficients here, they form a unitary, and it kind of has the nice property that all the absolute values of the entries of this unitary matrix are the same, 1 over square root of d. I guess the dimension is d. I had it somewhere up there. And so we write these kind of Fourier basis vectors, and the psi alphas are essentially the contraction of psi of our state with these Fourier basis vectors. So I mean, I can write them explicitly here. So it's the superposition of the square root lambda k like there, but with these weird phases. So that makes them kind of as orthogonal as I can make them because of due to the presence of the lambdas. And so Q is going to be this one. It's the sum of these projectors. It's an orthogonal basis, and those guys, they are just rank 1. So that's also an orthogonal sum. Both of them are projectors, and then you just calculate that the product is indeed psi. And so both of them, they suggest experimental procedures to measure these guys. Because I mean, here you just, I mean, obviously you have to know your target state, but then you can work out what those Schmidt bases are. Each of them just locally projects into the Schmidt basis, and they compare results if they got the same. If not, they reject the state. And well, similarly here, it's a bit more complicated. You need to measure the alpha head basis, and then depending on the outcome, the other guy needs to make a different measurement. And then you can.
Is it essential that psi AB is of full Schmidt?
No, of course not. I mean, like, okay, if it's not full Schmidt rank, then you have to extend the projectors in some well, you don't. Yeah, I mean, you just this D will be just
minimum of the dimensions.
Yeah, it will be. Yeah, well, I don't know. Actually, it doesn't. I mean, nothing goes wrong when some of the lambdas here are 0. That's kind of what I want to say. You just, I mean, it's just algebraic identity.
Yes, does this inequality imply some bound on inequalities relation automatically?
No. It's. I mean, this is not a Bell experiment. These are just.
Yeah, but it looks like you could get something out of this. This 2, right? I mean, there's a silent 2 here. Because there are 2 1s.
Yes.
I'm just.
I think it's a challenge. I mean, these are. It's suggestive. I mean, but actually, probably not. When you do this for the maximally entangled state, so let's go back. Let's waste more time. So, yeah, EPR. That's the one thing they got wrong. It's not an example of something that really, where really I mean, or rather, EPR. I mean, the discussion between Bohr and EPR somehow missed the point, because they introduced this notion of hidden variables, but they only talk about these observables. I mean, we translate this into a finite dimensional setting into 2 spins, but it is essentially equivalent. They talk about these X and Z and X and Z. And so that's on a maximally entangled state, that's a pair of 2 observables that has a local hidden variable model. So those are precisely measurements that do not lend themselves to violation of a Bell inequality. I mean, despite the fact that you have an entangled state. So that's the difference between certification, where you and non-locality test. Right? Okay. Certification is just okay. I mean, I have my quantum system characterized. I know which measurements I make, and based on the results, I can. I mean, in Hilbert space, I can locate my state. So it's a bit. Yeah. So if you do this construction for the maximum entanglement, you just get back this APR boom guy. So it's maybe not directly related to Benning points.
And this may say what about what you meant by fidelity test and experiment. There's chalk on the left.
Yeah, on the left. Okay.
On the left there, here.
There's chalk also there.
Look at me.
So yeah, what you would like is that this in an experiment, you would like to make enough measurements so that you can conclude with some confidence that this is true. You know, this is your true state. I mean, we assume that the quantum system is can be described by some density matrix, and we just run enough experiments to conclude that this here is less than or equal to epsilon. And so to do that, like one way you do this, well, okay, I mean, this is the same as trace rho 1 minus psi. Okay, so if you know enough matrix elements of rho by tomography, then you can just calculate this. And so the suggestion of Barbaresco et al. Is, well, you don't need to do this. All you need to do is, if you're really interested in this fidelity, in this particular one, given psi, construct P and Q, these are two local measurements, just do those two and run statistics, because also in the trace of of the true state with 1 minus P, that's data that you can extract by simply doing these few local measurements. And you get an upper bound on this 1 minus the fidelity in terms of these two expectation values for an arbitrary state. That was their idea. And I can say that kind of very nicely, this also generalizes to multipartite, even though it becomes a little bit more ugly. You need more and more, I mean, you need quite an exploding number of projectors, but and it becomes less experimentally convincing, let's say, but for 3 parties, I think one can probably still find somebody who is interested in that to run it now. Okay, so let's see. Wow, I'm really in classroom mode. I'm sorry, I think I was teaching too much recently, so what am I talking to you guys? So, now the second part, I want to talk a little bit about non-locality. And so that also has to go back to this EPR paper and Schrödinger's analysis of it. So in his reviews in 35, and then in more formal and more general way, Weisman, Jones, and Doherty much more recently, they talk about something called steering. The one system steers the other, and by which okay, so it starts from the following observation. We have some density matrix rho that describes the joint state. If we make the observation on the first system, so I just introduce some kind of language here, this X labels different measurements, like the X and P, or the different Pauli measures, and the A labels the outcomes of those. So if these are just, if this is Alice's measurement, so it's just a bunch of positive semi-definite summing to 1, then we can ascribe to this and to the actual state shared a post-measurement ensemble for Bob. And it looks like this. So this partial trace of rho with E tensor identity, well, that will be a positive semi-definite. And if I take out the trace, I get a probability of A condition X and a state. So that's the post-measurement state. And these kind of things, they are called in the more recent literature assemblages. Why they have these assemblages? Because they are decompositions of the reduced state of, don't I have this here? Well, maybe it's on some following slide, but I'm standing too close. So the sum of all of those guys is simply the partial trace of A of rho. So that's the same thing for all X. And so, yeah, what Schrödinger noted for the pure state, for the EPR state, and what we can also note for lots of mixed bipartite states, in general, these kind of assemblages cannot be explained as coarse grainings of a single ensemble that is sometimes called the hidden state model, in, I think, following Weisman et al. And so that's kind of going in the opposite direction. So like Einstein, Podolsky, Rosen concluded, okay, there must be this hidden variable. And but Oedinger look at this and said, look, I mean, the post-measurement state it was this. I mean, you said yourself, once I measure set one up, I can predict, or Alice can predict what the other outcome would be. In fact, she can predict, she can assign a state to Bob, even though he doesn't know the state, unless she tells him. So mathematically, everything seems to be fine. These decompositions, they cannot be obtained by simply some processing of a single convex decomposition of Bob's state. I mean, the state, once you go to the state, then you're lost. So if there's a hidden variable, it must be something behind it. And yeah, so that was 30s. In the 60s, eventually Bell took up this discussion again. And so he looked at it from the point of view, just very, very abstractly, I would say. Well, what can you actually experimentally access here? And so from what we take from the EPR setting is, well, there is this state. I mean, this is a very specific state there, but maybe it's not so important. We have some state, pure state ideally, and we have possible local measurements on L. So these are our X and P measurements, or whatever is required to arrive at EPR contradiction or paradox. And whatever the set of possible observations are, every observation of A commutes with every observation on B. That's because of the tensor product structure. And so for every pair XY, this is a probability distribution of pairs A and B. And they will be correlated in general because that's not a product state. I mean, that's the boring case. It will not a product state. So there will be some correlation. Given XY, there will be some joint distribution of the outcomes A and B. And this is what even Bohr would say, well, that's experimentally accessible. I mean, obviously there are different experiments, but they all relate to the same setup. You can just turn some knobs and that's it. And so after the analysis of Bell leads to this, well, this is just Born rule. And the analysis of Bell was, well, what EPR really wanted, this local hidden variable, can only describe joint distribution of this form. So there must be this unknown lambda, which I don't want to make any assumptions about, so it's kind of a different kind of symbol. It has to have a distribution because that's kind of the law of nature behind it, which I'm trying to discover. And then the local experiments somehow have a rule based on lambda and X, they give me an A, an outcome A. And based on lambda and Y, the other experiment gives me a B. And so the simple observation, well, in hindsight, almost trivial observation of Bell is these two sets that you get by taking the union over all possible experimental setups here and taking the union over all such descriptions, those are different. And Bell inequalities are witnesses to this. So the reason is that well, actually, I'm going to get there in a second. So it took a while, of course, like lots of false starts, but eventually Bell and then Clauser, Horn, Shimoni, and Holt, they got there. They found such a conditional probability distribution of the form of quantum mechanics that cannot be written in the local hidden variable form. And so the Bell inequality is basically just a linear combination of these observable probabilities, which, I mean, those I can learn by just running the experiment enough times. And so maybe I know the maximum of all local hidden variables, and or I have an upper bound, and it's a Bell inequality. And so that's then violated by quantum behavior of the form Q, this kind of thing. And so rather than writing such a thing down, let's do a little bit of mathematical reflection on these kind of things. So when you write, I mean, each of those behaviors, P of A, B given XY, that's just a list of numbers. They are probabilities, so they have to obey positivity. For each X and Y, they have to sum to 1. But then there are other conditions implicit, because for the so-called local polytope, I want to make a convex combination of these product functions. And so you can work out the number of extreme points. Those are precisely the functions, where A depends deterministically on X by a function, and Y is a function, B is a function of Y, so there should be Y over there. So there are these very large potentially large number of extreme points, but there is kind of the dimension of this as a polytope, as a convex polytope, is this one here. It's kind of this basically on the order of the number of parameters that you have, minus the relations you have to obey. And so that's obviously, fairly easily to see that this is contained in the quantum set. So all the things that you can write in this way. And I'm deliberately vague about this here because I don't want to go into it. There are different versions of this set that are contained one in the other. And I'm just interested in the last, in the biggest one that we consider in this kind of business, the set of no, that's also a polytope of no signaling behaviors. And that comes from the observation that if you sum over A here, you get something which doesn't depend on X. And if you sum over B here, you get something that doesn't depend on Y. And so those are the no signaling conditions that are automatically fulfilled by quantum mechanics. That's something that EPR and Bohr and Schrödinger were very well aware of, that by just choosing different measurements on one side, you cannot actually give a signal to the other side. So this kind of signal must be something very subtle if it's going on. It's not visible. Okay, so here are two things about this that connected to entanglement. Or three. So the first is a very simple observation. If rho is a product state, well, then all of those P of A, B given XY, they are product distribution. If it's a convex combination of product states, well, I mean the convex hull of those. So that means if I have a separable rho, then this guy here, regardless of the measurement, will always be a local, will always be in L. And there are kind of two attempts of kind of completing this observation. Well, one of them is sort of just the converse. If the state is sufficiently entangled, I mean, in the case of, so this is attributed to Nicolas Girard, every pure entangled state, every pure state is not a product state, does violate the Bell inequality. So that means there exist local measurements such that this PAB given XY is not in L. And then you might wonder, okay, maybe every entangled state violates the Bell inequality. And so famously, Reinhard Werner here exhibited states that are entangled, not pure, obviously, because of this limitation, that don't violate any Bell inequality. Whatever the local measurements are, you can take the family of all local measurements, so X and Y are continuously parameterized, it's in L. So that's kind of, I mean, this is a topic of ongoing research, I would say, where I'm not very much involved. It's about, finding the boundary where you have entanglement, but still locality and so on and so on. Before I only talk about non-locality, let's discuss a little bit entanglement as a resource, because that's kind of quantum information. That's the third phase, I would say, of quantum information of entanglement. And interestingly, I would say what changes there is that in the foundations, it was always very important. Oh, we have these two space-like separated regions. They only do local actions and they don't talk to each other, except at the beginning of the world, before the experiment starts. And so that's kind of limiting. It's very good for philosophy, but not very good for quantum technology. You have to allow a little bit more. And so the very good move is to extend from local operations to a local operation and quantum communication. In particular, local operations that are not just measurements, but let's say partial measurements or some unitaries. And so once you go there, you get a very, very interesting class of transformations. I mean, it's kind of, at first, LOCC is described as a protocol. It looks more like a lab book thing. It's do this, then send the following message. If the other side gets this message, do that. It's another thing. So it's a kind of whole instruction. It's an algorithm. And you can draw pictures like this kind of about the information flow. You have your entangled resource. Maybe Alice and Bob, they have their own systems here. And then one of them does something. And this something is an instrument that gives you a classical outcome that can be shared with the other party. And then based on that outcome, the other party has another instrument and so on. And they send information back and forth. At some point, they decide to stop. You integrate all of this. You get a big instrument. And you can, I don't know, for example, forget about these classical messages here. You just get a big channel from A prime, B prime to A prime, double prime to B double prime. That's kind of the net effect of this algorithm. So this set of algorithms defines a class of maps, of channels, of TP-TP maps. And those we also call LOCC. So I mean, we tend to confuse them. It's a bit like in computability theory that we confuse the algorithms with the computable functions, which you shouldn't, but it's kind of a common thing that we just lump them together. And so why is that interesting? Because the communication unlocks certain things in the entangled state that were not really there before in the EPR kind of setting. For example, famously teleportation by Bennett et al., where you have a pure entangled state and Alice measures that state together with her target state, and after communication and some local unitary of Bob. So that's maybe the simplest kind of LOCC, where I do a measurement, but not a non-measurement, actual quantum transformation here. I get the same state out here on the other side. So one EPR pair plus 2 bits of communication is kind of equivalent under these LOCC algorithms to the transmission of 1 qubit from one side to another side. So that's one of the motivations. I mean, there are plenty of other things that we can do with this entanglement once we allow this kind of local operation in classical communication that I didn't write here. For example, measurement-based quantum computation with multi-party entangled states. Another observation comes from the fact that if we look at those separable states, those are precisely the ones that I get from this class of operations, LOCC, when I start from no correlation at all. If I grant you in the experiment local product states, then by just doing those LOCC, you will always get separable states, and you will get all of them. And so, yeah, the last one is kind of the observation a posteriori that the channels that we get here, so the CPTB maps that induced by this LOCC, as in the previous picture, that goes from a bipartite system to another bipartite system, it turns out to be the natural class of transformations of entangled states, to play with them. If you're given a state, you want to get another one, well, with unrestricted quantum dynamics, there's no limitation. You can just go from one state to another, and that's it. Okay, so that's kind of the definition, or well, kind of the definition I didn't even dare to write because it would take me several slides, but kind of extrapolating from this algorithm picture, you get this class of channels, and that we found out over the years that this is, despite the fact of being very beautiful, it's also very hard to capture what it is. And like one of the details about this geometry, it's a convex set, but it's not closed. I mean, as soon as the dimensions of this A, B, and A prime, B prime are sufficiently big, not very big, but just have to avoid trivialities, this set is different from its closure. I mean, these are, whatever topology you choose on the CPTB maps, it's a subset, and you just take the closure in there. So that motivates various relaxation. A very simple one that you can observe is that all of those guys here, they can be written with tensor product Krauss operators. That's kind of the Krauss decomposition of the CPTB maps. Not all of them, but they will exist one that can be extracted from the LOCC algorithm of product form. And so that is a closed set, but we also know that it's strictly bigger than the closure of LOCC. So I think the very first paper that showed this was something titled non-locality without entanglement. And it's not non-locality in the sense of EPR et al. It's kind of wide interpretation that showed the difference between, well, maybe one of the most striking differences between the two sets. I think it's not so difficult to see why they must be different, but okay, that's CPT.
Different they are?
You mean like in the sense of convex geometry? I don't think we have very big insight there. Yeah. Well, this is okay. I didn't even think about this for the talk. So this is about this kind of comparing volumes. Yeah. So this step is a convex volume sitting inside all the CPTB maps, and then LOCC is another convex volume inside there. That would be very interesting to know, like the asymptotic growth of the relative volumes. But
Volume ratio is
I don't think. I mean, for the SEP, that's easier because I mean that's probably derivable from known things, because that corresponds to that when you look at the Choi matrices, it's just a fine section of the Choi matrices, of the separable Choi matrices here. So it's probably similar. But yeah, LOCC inside here, I think we don't really know anything.
It's somehow NP hard to decide whether Choi matrix comes from a LOCC.
LOCC.
It could be another hard in some way.
it's already NP-hard to decide if it's separable. If it's a separable superoperator, because that is equivalent to Troy matrix being separable, and that is by Gurwitz, we know that's NP-hard. Again, for LOCC, I think, so if you say, oh, it's a promise problem, I know it's separable, like maybe you're given a separable decomposition to start with, and then you want to decide whether it's LOCC or LOCC approximable. I don't know. I mean, there is the annoying issue. One of the reasons why it's so difficult is that there is this back and forth. And in my picture, I had to stop at some point. But I mean, in the definition, you take the union over any length of protocols.
So the non-closure is related.
Yeah, exactly. Non-closure is related. Exactly. For each finite number of iterations, you get a closed set, and the union of those for like number of rounds growing to infinity, that is not closed. So yeah, I think like this paper I wrote with Eric Chitamba that I cite here, it's mostly a document to like how magnificent our ignorance is about this set, or how magnificent this set is, so that we are so ignorant about it.
But you also have this superset of it, which are these now separability preserving.
Yes. Yeah, so that's one of the reasons to introduce that, because it's kind of at least mathematically a bit easy to handle. In practice, that's still not that very useful, but still.
And there's the PPP versions of that.
Yes, yeah, exactly. I didn't even dare to mention it here. Indeed. Yeah, so once you are in this kind of resource framework that you have some transformations that are kind of allowed by the rules, like this local operation. Well, okay, then you can focus on specific ones, and two that turned out very, very early in this business in a paper of Bennett et al. From, well, Bennett, DiVincenzo, Smolin, and Wouters from quite a while ago now. It's distillation and dilution. So we know already that the maximal entangled state, the EPR state, that's kind of an interesting one. So it turns out this is definitely, we want more of that. And so we would like to know LOCC procedure that give us that kind of state, and vice versa. We would like to go from this state to a target state, which if this state is not separable, we will need some entanglement in addition to the LOCC to make it. And so if you, I mean, what inspired by Shannon theory, by information theory, we allow some small perturbation here, and we also allow some kind of asymptotic limit here. So if we have many copies of the state and we want to make many copies of EPR pairs, there's a question of the rate, how large this R, this ratio between the numbers can be, and how small the ratio can be here. And so those two quantities, they are kind of in the Shannon theoretical theory of entanglement, they are very basic, but they've been around since those days. So the distillable entanglement, that's the supremum of the rates of all such protocols where n goes to infinity and epsilon goes to 0. So that's the approximation there. And the entanglement cost, that's the infimum in the second kind of protocols over all LOCCs. So that's well defined, but obviously by our ignorance of LOCC may be a bit hard to get. Well, the first thing is kind of the starting point of all this is why actually there is even a resource theory of entanglement, is because for pure states, those two things we know it, there's a closed formula and they coincide. It's kind of maybe the one miracle that got so many people to work on entanglement theory in this setting. So the distillable entanglement from a given pure state and the cost to reach a pure state from EPR pairs is given by the reduced state entropy, the von Neumann entropy of the reduced state. So this calls for the pure states, it's often called now the entanglement entropy. And I just want to point out a kind of a subtle asymmetry that still persists here, which is, it goes back to the Bennett et al. Paper, well, another Bennett et al. Paper from '96. The distillation doesn't actually require any communication. So this is done by just local partial measurements and unitaries. The dilution, they needed communication, square root n, and it was eventually shown by Harrow and Lowe and also by Patrick Hayden and myself about the same time that this is necessary. So you can, for the dilution, it's really annoying to turn the state into a less entangled state. You need to communicate, even though it's lower order than I don't know what, well, I don't know what this is good for, but yeah, fine. So for the cost in general, we have a formula too. So this kind of, there is this kind of thing. It's a typical quantum Shannon theory formula. It's a so-called regularization limit of a quantity that is kind of well behaved. So there is this E sub F, that's entanglement formation of a state. That's the minimum average entanglement entropy over all convex decomposition into pure states. And well, it turns out this is not additive. So you kind of EF of rho tensor rho can be smaller than twice EF of rho. And so you take this infimum here, that can then be strictly smaller than, so E cost is strictly smaller than EF in general. And so this is very hard to compute. I mean, well, in general, this is hard to compute. We mentioned this, so it's even NP hard to decide whether it's 0 or not for a given density matrix. This infimum, well, as this n going to infinity, so it's basically no formula. It could be uncomputable for all we know. But at least we have the following. We have this kind of statement of faithfulness that goes back to Young, Michael Horodecki, and Barbara Sinner-Gradke, I think. So that the cost is positive whenever the state is entangled, and it's 0, of course, if the state is neutral. So that kind of is an important piece of intuition that at least is correct, that survives this kind of, all this kind of asymptotic analysis. For the distillability, we really have very much less. We don't have a useful formula. We have this kind of lower bound. This was called the hashing lower bound. It was conjectured by Bennett et al. Also in this founding paper. And famously, Horodecki has observed that there are bound entangled states. There are entangled states that have distillable entanglement 0. And okay, one of those open questions that have been around ever since then, since 25 years ago, is whether there is bound entangled states that have non-positive partial transpose, because the trick was to say, well, if the state is positive partial transpose, so that's this here, then it cannot be distillable. And so, yeah, what you would be interested in is, for example, then upper bounds on these kind of quantities, computable upper bounds, but the ones I'm going to show you are all not really computable. They're theoretically interesting, but they are also kind of not so useful. So, for example, a very important one is the relative entropy of entanglement. Actually, this is not so bad here, because this is, I mean, conceptually, probably this remains one of the most important ways of thinking about monotones. We have this set of separable states, and then we use some kind of contrast measure. So it turns out a good choice is the quantum relative entropy, this one here, and you minimize that relative entropy between rho and sigma over all separable states. And so that turns out to be an upper bound on the distillable entanglement. And so does, by definition, by the fact that distillable entanglement involves this many copy limit, so is the regularized relative entropy, which also we know it's strictly smaller than the single copy relative entropy. So again, eventually we learned something about this regularization limit. It cannot be that rho is entangled and this is 0. That's an important sort of, I mean, satisfying insight, but also a bit annoying, because it means that you cannot use this kind of upper bound to prove that something is bound entangled. If rho is entangled, well, this will be positive. This is your upper bound, even whether you can compute it or not. Piani found a lower bound that is on this regularization that is positive if and only if the state is. So it's faithful in the sense of the entanglement of formation. And then you have other ones, like, I mean, I'm going to the zoo of entanglement measures, which I was trying to find some references about the zoology, but there's really not that much around recently. Squash entanglement, maybe, I don't know, that also is an upper bound. I mean, it's defined in terms of entropies in a more complicated way. Could I talk about this a little bit? Okay, I mean, there's kind of lots of interesting computability questions associated with the squash entanglement. So these problems we have here with the relative entropy or the entanglement of formation, there the issue is that they are not additive in the many copy sense. So we have to regularize. We always have to take this infimum here. The squash entanglement turns out to be additive on this kind of tensoring many independent copies. But it has a different problem that kind of is sort of maybe the price we have to pay for this, which is in the definition, in taking an infimum over all tripartite states with a given ρ B as a marginal, and then we minimize something called the quantum mutual information, the conditional mutual information. So it's just a certain combination of entropies, four different entropies of the three-partite system. And so that also turns out to be an upper bound on the distillable entanglement. And also this one is faithful. So again, even when you can compute it, it's kind of ultimately, this is not going to be a tool to prove this kind of bound NPT bound entanglement, because it's for entangled state it will be positive. And so
Yes, there was also like the reverse relative entropy of entanglement, right? Where you have minimization on the other side.
oh yes.
And well, in statistics, you use it quite a lot now because you fix the right-hand side of entropy and then
Yes.
minimize on the left. But then somehow disappear from by Isert.
Out and yes.
And also it satisfies some good properties like additivity, because now, of course, you're minimizing on the other side.
Yes, maybe that's true. I think it's sort of in terms of value, it tends to be the bigger one. That's the thing. So like if you want a sort of a tight upper boundary, so let's think about proving bound entanglement or almost bound entanglement. I think it sort of tends to have large values rather than small values.
It was abandoned.
Yeah.
Anyway.
Well, you need a full rank row to be even finite value. I mean, no, that's not true.
Minimize, no?
No, you minimize. Yeah. Well, okay, it still can be infinite. So I think I'm nearing the end of my little review of this bipartite Shannon theoretical entanglement. So I just want to introduce yet another interesting kind of distillation, I mean, the secret key distillation. So that I think that sort of in the literature you can trace this back to Eckert to base cryptographic security on the presence of entanglement between two parties. And then I mean, this kind of model is very well developed in Renner's work since the early 2000s. So cryptography requires another party. We need an eavesdropper. So what we assume is that, okay, Alice and Bob, they have this state ρ AB. The eavesdropper has some other information. And so the best you can imagine is that Eve has just a purification of this state. It's just some pure state whose partial traces is ρ AB. And then the idea is, well, this protocol that Alice and Bob execute as the key distillation protocol, they have to communicate. This communication, this will be in the open. This will be public communication. So the eavesdropper gets a copy of that. This is fine because classical communication can be copied. And so at the end of the day, so we start with this pure state. At the end of the day, we get some kind of mixed state here that for Eve also includes all this classical communication. So Eve is not deleting that. She wants to extract information from this. But the target should be that you are getting close to perfect classical correlation and tensor product with Eve. That's kind of, these are the two cryptographic requirements. You want perfect correlation, but it's just classical. It's just a secret key that you can write down somewhere secretly. And it should be uncorrelated from Eve, from whatever Eve has at the end of the day. And so you can again define an optimal rate when you have many copies here and you want a large dimensional system here. So this D should be like exponential in N. And the optimal rate R, has this name, this distillable secret key, which has the same problem as the distillable entanglement, that we don't really have good characterizations of those things. So I just want to the reason why I introduced these particular measures before is because they go together well with the secret key. So it turns out all of those numbers that I introduced, the cost, the squash entanglement, and the relative entropy, they are actually not just upper bounds on the distillable entanglement, they're also upper bound on the distillable key. And that's kind of a beautiful distinction, the first one, because it's also again 18 years ago now, Horodetsky and Jonathan Oppenheim, they showed that there exist bound entangled states, so they have a distillable zero with positive secret key rate. And so by now we understand that those are actually quite abundant, at least in the sense of states. Maybe experimentally, they're extremely highly mixed states, of course. But yeah, conceptually, that was very interesting development. I mean, just like this one, for this one, we don't really have any useful formula to characterize it. And we know that these two guys here are not comparable. So in the sense that there are states where one of them is much bigger than the other and vice versa. It cannot be that one of them is 0 and the other one not because of the faithfulness. They are all they're all strictly positive for the interesting entangled states. And so, yeah, the kind of open questions that have been with us forever, and then some people in here even have attempted recently to get a little bit back to it. Does there exist non-positive partial transpose bound entanglement exist? And maybe an even more radical idea: are there entangled states that have 0 key? So we have no workable criterion for this, actually. This, unlike the bound entanglement here, where we have this positive partial transpose, there's nothing, we don't have anything that would prove that the key rate is 0, except that if you observe rho is separable, then it's sticky. I should say, actually, I forgot to mention this. These papers here, this one paper and the subsequent, they do suggest candidates for both of those things. I didn't write here, but maybe we can talk about this in discussion in the afternoon, because I really love to. I mean, like it's years I haven't thought about this suggestion from Borodetsky and Oppenheim. Okay, maybe I should find a way of finishing, because I mean I realized I took much more time than I thought I would for the little stuff I have to say. Yeah, so I just want to say a few things about multi-part entanglement, because I think there's also like several people here that kind of find this more exciting. The fact is also they're more frontiers there that are maybe accessible. So I would say a lot of the theory focuses on pure states, and one of the motivations is that, well, you can always purify a state by introducing another party. Then of course you have to restrict to LOCC where that party doesn't participate in any meaningful way. But still, I mean, this seems to be sort of a better way of thinking about it than just attacking head-on big states. It's kind of there's more structure here. Obviously, you can always choose kind of local computation basis and expand your state with some coefficients. But the point is, we would like to get things which are in some sense invariant under this basis choice. Just like in the bipartite case, there we can find the Schmidt basis and then via the singular value decomposition and Schmidt coefficients. That all comes from matrix theory, from singular values, ranks of matrices. Those behave very well under tensor products. If I, like in this information theoretical limit, I want to have many copies, well, I only have to do the work once. And well, for n larger than 3, both of those things, they don't really generalize in a good way. They do generalize in some way mathematically, but they lead to each to their own catastrophe. So for the Schmidt coefficients, well, ultimately these are important simply because they are the local unitary invariants, the SUD1 times SUD2. That's the symmetry group invariance. Obviously, you can do the same thing here. You have the product of local unitary groups. You can try to work out the invariance. Well, okay, you can try, but you will not come to an end because the number just explodes very badly with the dimensions. Kind of 2 is the case where it behaves well. Yeah, yeah, exactly. I'm going to finish. And if you're just looking at the rank, at the Schmidt rank, so the number of terms you need, that's kind of the rank of the coefficient matrix in the bipartite case. That's called the tensor rank in the general case. That's also a very, very weird animal that has lots and lots of peculiarities. And maybe I show a little example here. So, for example, in the 3-party setting, there is this GHZ state of the 0, 0, 0 plus 1, 1, 1 superposition, and this so-called W state that has 3 terms. So this is indeed, these are both minimal in the sense that there is no decomposition with fewer terms. So they have tensor rank 2 and 3. However, W is actually in the closure of the rank 2 states. And this happens because you can make a superposition of 2 states that are kind of almost the same, like very parallel. And so W is actually in the closure of the tensors of rank 2. And so you have another notion of which is the border rank, which is like you're just looking at, can you approximate the state by ranks of rank R tensors? So both of those are, for example, not multiplicative on the tensor products. They're not very simple quantities. And so one of those questions that I mean, maybe this is just my ignorance, but I think it's kind of interesting to know what is the maximum rank that can appear among all states. So in a bipartite setting, it's simply the minimum of the two Hilbert space dimensions because it's a matrix. So the maximum rank is the smaller side of the matrix. In three-party, D1, D2, D3, that's some function of this. And I mean, we know the order, but I don't think it's known what is the actual maximum value of this rank, or what are the possible integer values of this rank in a given setting. And yeah, so then when you try to emulate this information theory, then you say, let's look at pure states, whether I can convert them into some nice form, reversibly, like I can bipartite states convert them into EPR pairs. Well, it's clear that you cannot, when you think about it for a minute and you realize it's very clear that you cannot interconvert all states into each other reversibly. Because it would require that there's one single state that I can go from every state to there and come back. Well, look at EPR pair between two parties tensored with a local state and a third party. So that means these two are entangled, but not in A and C are a product state, and B and C are a product state. So from there, you cannot go here by any number of copies, and you cannot go here. So for an asymptotic normal form that emulates the Bennett et al. Entropy of entanglement, we need a set. So what we want is we would like to convert n copies of psi by local operation classical communication into something like this here. So each of them is a multi-party state. Actually, sorry for the n. N up there is the number of parties. Here down here is the asymptotic number of copies. So that's very bad. This should be a k here. I don't know. Each of them is a multi-party state, and you have some number of copies. So you have these characteristic rates. And this set here, well, I mean, that's ideally should be finite set, but nobody knows whether such a thing exists. I mean, there are plenty of results that show that beyond these three states, you definitely also need the GSZ state. In three parties, you need at least one further state, and so on. I mean, there are kind of negative results. I think the general suspicion is there is no MREX. There's no minimal reversible entanglement generating sets.
Quite a lot of work by people like Barbara Krauss.
Yeah, they have a different take on it. So yeah, there's yet another class of transformations, this stochastic LOCC, and also if you give up the reversibility, I mean, this is like that's the key. I mean, like the pure states, I mean, basically the message says you have to give up the reversibility, and well, asymptotic reversibility in any case already for pure states.
One could also go like to full-blown like resource theory and say, okay, I have operations that only keep free states free. Like resource morphisms.
So yeah, I mean, this reversibility, maybe that's overrated. So you could say, well, let's just do the usual thing. I mean, we know we need ETR pairs. We know we need GSZ states. We need kind of interesting states. So you can look at different protocols that and achievable rates that turn a given multi-party state into one of those useful ones. For example, just bipartite entanglement where n-1 parties help the remaining two to get the maximum amount of EPR. So it's entanglement of assistance and so on. And yet another direction is you just don't want to talk about arbitrary states. You want to talk about nice states. So for example, I mean, going back to EPR, they had this beautiful stabilizer structure. Well, that turns out it generalizes to n-qubit states. You have this rich structure of simultaneous eigenstates of commuting products of Pauli matrices, and that includes error correcting codes and lots of other interesting states, and in particular these states that we have seen before, not the W state though. Okay, so to classify, so maybe this is kind of I'm trying to get there. So to classify the states, you need entanglement monotones. So I want to skip over these technicalities with the continuity. So it turns out for pure states, those reduced state entropies, they are actually all good numbers that one should look at, and they are also nice because they are just computable. You just compute the partial trace and calculate the entropy. There is also relative entropy numbers, actually many of them, because you have to minimize over different different sets of separable states, like depending how separable they are. There's in multi-party, there's sort of a whole zoology of separability. So that gives rise to different numbers of those. But again, in the information theoretical limit, you need to regularize. And so I would want to end kind of with something that I started with, namely with the uncertainty thing of Heisenberg. So in the all of this entanglement theory that kind of got lost a little bit. And you can make the argument that that's somehow because we don't, well, part of it is because we don't talk really about about measurements so much, but we don't talk about states. But you can sort of trace this uncertainty principle in the presence of something that Charlie Bennett called the monogamy of entanglement. Namely that if A and B are entangled, then A and C cannot be entangled in the quantum mechanical sense. And that's sort of true in the qualitative sense. If A and B are in a pure entangled state, well, A and C must be in a product state. So quantitatively, that's hard to capture. If you want to say, well, the more one pair is entangled, the less the other is entangled. But okay, there are some examples of this type. There are sort of inequalities for certain entanglement measures, like the force entanglement. But I think that ultimately that was all misguided. I mean, we were all kind of blinded by some paper by Bill Wouters, where he showed a relation like this for some very simple qubit systems and for a very specific choice of entanglement measure that only makes sense for those qubit systems. We wanted monogamy to be something like this, like a limitation trade-off between this. Well, I would like to ask you to think of this more generally. Really, entanglement of monogamy is about the constraints that those different entanglement monotones impose on each other. So among those, one of the most important one in the multi-party setting are those local entropies. So the reduced state entropies, they're the only ones that we can actually calculate. And so they obey natural inequalities. These are known inequalities. These are fundamental inequalities of information theory, subadditivity and strong subadditivity. And from classical information theory, we know that there is an infinity of such inequalities that hold for the Shannon entropy. That is a special case of the phenomenon entropy. And so from this investigation comes the conjecture that something like this holds. This is this inequality of Zhang and Young that is proved for the Shannon entropy, and we suspect it might be true for the von Neumann entropy as well, plus an infinite hierarchy of similar inequalities with more weird coefficients here. There's a 2, but then there are other rational coefficients. So those, I would argue, I mean, well, first of all, they have to be true, but those, I would argue, those express the monogamy of entanglement, truly. It's just about how the different monotones restrict each other. It's not about this measure or that measure, and whether the sum is bounded by some other value. You have to discover the bound. That's what it is. And oh yeah, finally, okay, great, thanks. So that's the end of the talk. Good.